Welcome to AI Paper Podcast.
Right.
Today, we are tearing into a paper called tttLRM. That's test time training for long context and autoregressive 3D reconstruction.
From the folks at UPenn, Adobe Research, and UCI, and honestly, it's a game changer.
Yeah, it really is. And look, if you are building 3D systems right now, you already know the bottleneck we're talking about here. Standard feed-forward models use transformers.
And because attention scales quadratically, you hit a massive memory wall.
Exactly. The second you try to scale up your input views, it's over. But tttLRM bypasses that entirely. It rips out standard attention, replaces it with a test time training layer, or TTT, and compresses massive streaming image sequences into what they call fast weights.
Which results in linear computational complexity.
Right.
It is a fundamental shift in how we handle spatial data. The results they published are just staggering. This architecture reconstructs high-resolution 424-pixel, explicitly decoded 3D Gaussian splats.
Or NeRF triplanes, right?
Mm-hmm. Yeah, exactly. NeRF triplanes if you prefer from 64 or more input views. But the kicker here is that it does this autoregressively.
Meaning it processes a streaming video feed basically the same way an RNN processes a string of text.
Precisely. If you give it a 32-view scene, it achieves superior novel view synthesis in 7.2 seconds. Compare that to traditional 3D Gaussian Splatting optimization, which takes about 13 minutes for that exact same scene.
So we are finally looking at a bridge between the sheer quality of neural rendering and the speed of real-time explicit 3D systems.
We really are.
So that is the 60-second download if you just needed the headline. But for the ML engineers and spatial computing researchers listening with us right now, let's really unpack the mechanics here. We all know the current landscape.
Right. Methods like NeRFs and 3D Gaussian splatting produce jaw-dropping renders, but
They're completely held back by per-scene optimization. I mean, we've all been there, right? Staring at a progress bar, waiting minutes or even hours for gradient descent to fit a single room.
just praying your loss doesn't nan out right at the end. Oh, the absolute worst.
It's incredibly frustrating. And more importantly, it makes those methods totally useless for real-time applications. If you're building an autonomous drone or, say, a robotic agent, it needs immediate environmental understanding.
It can't pause for 10 minutes to calculate the geometry of a hallway before moving.
Exactly. Now, the field has tried to solve this with large reconstruction models, or LRMs. You've probably seen papers on GSLRM.
Yeah, those models are feed-forward, meaning you pass the images in and you get the 3D representation out instantly in a single pass.
But they have a fatal flaw. They rely on standard self-attention mechanisms.
And we all know what happens to self-attention when the sequence gets long. If you double your input frames from, say, 4 to 8, your memory footprint doesn't just double.
Because it scales quadratically, your memory footprint quadruples.
You're suddenly throwing COD out of memory errors on an 80 gig A100 just because you wanted to look at a chair from a couple of extra angles.
It's painful.
Whoops.
Those standard attention models completely max out at around 4 input views. The memory footprint just explodes. And 4 views is nowhere near enough to reconstruct a complex, real-world room full of occlusions, overlapping objects, detailed geometry. You need dozens of views for that.
You really do.
Now, there was a recent prior state-of-the-art feed-forward model called long LRM that managed to push this limit to 32 views. But if I'm trying to use this for a real-world system where the camera is constantly moving, I can't just stop at 32 static frames. Why does long LRM still fall short when we introduce continuous streaming context?
Well, it really comes down to the bi-directional attention layers long LRM relies on. That architecture works fine if you have a fixed finite set of 32 images. But it completely prevents the efficient processing of streamed context.
Because it's trying to look backward and forward at everything all at once.
Exactly. You cannot easily append new views on the fly without recalculating massive computationally heavy attention matrices across the entire history of the sequence.
Which is just a non-starter for real-time video feeds.
Right. And we should also contrast this with implicit latent models like LVSM. Those models have incredible novel view synthesis quality, but terrible rendering speeds.
Right, because they lack an explicit 3D format like Gaussians or meshes. With an implicit model, you have to run that heavy neural network over and over again for every single pixel you want to render on the screen.
Exactly the problem.
Yeah.
So the field has been stuck between a rock and a hard place. We desperately needed a model that possessed linear complexity to handle infinite context, but that still output explicit 3D representation so we could actually render the scene in real time.
So entered tttLRM. Before we get to these magical fast weights, how are we actually prepping the data here? Are we just tokenizing standard image pitches, or is there a twist for 3D?
The visual pipeline starts relatively standard, but with crucial spatial context. You take your posed input images and you concatenate them channel-wise with their ray embeddings.
And those ray embeddings act as your positional awareness, right? They tell the model where the camera is and what direction it's pointing.
Exactly. Then you patchify them. They use an 8x8 patch size here and pass those patches through a lightweight linear layer to tokenize them into a sequence. But this is the exact moment where the architecture completely deviates from your standard transformer.
Right. Instead of throwing those tokens into a massive self-attention meat grinder, we get to the core innovation, the large chunk test time training blocks, or LCT blocks.
This is where it gets brilliant. The visual tokens are used to update the fast weights of 24 LCT blocks. These blocks have a hidden dimension of 768.
And by doing this, the model achieves linear complexity.
Yes. Instead of every single token attending to every other token in the sequence, the visual tokens are updating a shared internal state. These fast weights effectively act as a fixed-size compressed neural memory for the entire 3D scene.
And to continuously update those fast weights, the authors use the muon optimizer. For anyone who hasn't played with muon yet, it's an orthogonal optimization method that's been making waves recently for updating hidden layers incredibly efficiently.
It's perfect for this kind of inner loop optimization.
So the visual tokens are flowing in, the muon optimizer is updating the fast weights. But wait, if the visual tokens are constantly changing the weights, how do we get the 3D data out of this memory without messing up the state we just built?
That is the critical engineering hurdle they solved with the virtual tokens querying mechanism.
Okay, how does that work?
To extract your 3D geometry, say a 3D Gaussian Splatting representation, the model uses a completely separate set of virtual tokens. Think of these as representing virtual camera views.
Got it.
You pass these virtual tokens into the model to query the updated fast weights. But the crucial detail here is that these queries only apply the weights. They do not update them. The internal state remains perfectly intact.
It's like reading from a database without locking or modifying the tables.
That's a great way to think about it. Once the queries have extracted the necessary information from that neural memory, a linear token decoder transforms those updated queries into explicit Gaussian parameters. We're talking RGB color, scale, rotation, opacity, and depth.
And what I love about this is that the decoder isn't some monolithic hard-coded thing. The authors proved you have massive flexibility here. If your downstream pipeline happens to require a NeRF instead of Gaussians, maybe you need continuous volumetric rendering for a specific lighting effect, you just swap the decoder.
Right. The exact same fast weight latent space can output triplane features for NeRFs. It's a universal implicit representation that decodes into whatever explicit format your engine needs.
You are totally decoupling the scene encoding from the rendering format. Now, if the architecture is this elegant in theory, we need to look at how it operates in practice. The real game changer for spatial computing here is the autoregressive capability.
Because of this fast-weight architecture, tttLRM can treat 3D reconstruction the same way an RNN processes text.
Let's break down how this autoregressive streaming actually works for you, because algorithm 1 in the paper is fascinating. If you have 64 high-resolution views, you don't process them all at once.
No, even with linear complexity, that's a massive wall of tokens.
Instead, the model handles incremental mini-batches, say 4 views at a time. It ingests those 4 views, updates the fast weights, and immediately predicts the Gaussians for the new query views. Then it simply grabs the next 4 views, updates the fast weights again, predicts more Gaussians, and merges the output.
And that continuous state update is absolutely vital to the quality of the geometry. The authors ran a very revealing ablation study on this. They tried a naive predict and merge strategy.
What did that look like?
In that setup, the model predicted Gaussians for batch A, then wiped its short-term memory, separately predicted Gaussians for batch B, and just mathematically merged the 2 sets of 3D points at the end.
I can imagine that looked like a complete mess. Floaters everywhere, Z-fighting, disjointed geometry.
It failed completely. It couldn't correct past errors or resolve occlusions effectively. If a chair was partially blocked in batch A but visible in batch B, the naive merge just created a scrambled artifact.
So the memory has to persist.
The continuous fast weight update is required because it allows the model to continuously refine its internal understanding of the geometry as new information arrives. It essentially corrects its own mental map before decoding the final Gaussians.
It is building a cohesive world model, not just brute force stitching together point clouds. But let's talk about the hardware reality for a second. Even with linear complexity, processing millions of tokens for high-res images to train a model like this from scratch requires immense compute.
Oh, absolutely.
The memory wall during training is still a huge obstacle. How did they actually fit this on a cluster?
This is perhaps the most impressive engineering feat in the paper. They utilized a brilliant implementation of distributed sequence parallelism.
If you've ever tried to train a large model across a multi-GPU cluster, you know the communication overhead usually kills your efficiency.
You can't just fit 64 high-res views onto a single chip. So they designed a highly optimized workflow. Step 1. The tokenized input views are partitioned or sharded along the sequence dimension across all available devices.
So GPU 1 takes the first chunk of tokens, GPU 2 takes the second, and so on. But they all need to share the same understanding of the scene.
Right. Which brings us to step 2, synchronizing the fast weights. And here is why this architecture is a masterclass in distributed systems design. The fast weights have a fixed, manageable size. They aren't a massive attention matrix.
Right, they're constrained to that 768 hidden dimension.
Because they are relatively small, they can be synchronized across the GPUs via PyTorch Distributed Data Parallel, or DDP, with minimal communication overhead.
So instead of passing millions of tokens between GPUs, which would choke your bandwidth, they are just passing this compact, updated neural memory state.
Exactly.
Right.
Once those fast weights are synced, step 3 is that each GPU independently predicts the 3D Gaussians for its assigned virtual views.
That's beautifully efficient.
Step 4. An all-gather operation combines all the predicted Gaussians from the different GPUs to form the complete 3D scene. Finally, step 5. Each GPU renders a subset of novel views, computes the photometric and depth regularization losses against the ground truth, and an all-reduce operation backpropagates the gradients globally across the entire cluster.
It's incredibly elegant.
Yeah.
That sequence parallelism is the key that unlocks the scaling laws for these reconstruction models.
Right.
You can scale to virtually any sequence length as long as you have the hardware to shard it across.
Exactly right.
Now, another thing that caught my eye is how they actually got this model to converge. They didn't just initialize the weights randomly and cross their fingers. They used a fascinating training shortcut.
Initializing tttLRM with pre-trained weights from large view synthesis models, or LVSM.
For anyone training large visual models, this is a crucial detail. Why does transferring knowledge from a 2D implicit novel view synthesis task matter for a 3D explicit generator?
Because it provides an incredible inductive bias. LVSM has already spent thousands of GPU hours learning how light works, how occlusion works, and how 3D geometry realistically projects onto a 2D plane.
Just like giving the model a crash course in physics before you ask it to build a house.
Precisely. By initializing the LCT blocks with these LVSM weights, it skips the hardest part of training from scratch. It drastically accelerates early-stage convergence. Within just a few thousand steps, the PSNR peak signal-to-noise ratio skyrockets compared to training from a random initialization.
And it fundamentally improves the final rendering quality across both the Gaussian splatting and triplane formats.
It does.
The inductive bias of 2D synthesis perfectly maps to explicit 3D generation. Let's dive into the hard numbers, because we know the benchmarks are what ultimately matter when you're choosing an architecture.
They definitely put tttLRM through the ringer.
They evaluated it against heavy-hitting optimization methods, standard 3D GS, MIP splatting, and scaffold GS, as well as the feed-forward baseline long LRM. This was across the DL3DV140 and Tanks and Temples datasets.
The leap in performance is definitive. Let's look at the 32 view setting on DL3DV140. tttLRM hits a PSNR of 25.07, and it does that in just 7.2 seconds using a single A100 GPU.
Wow.
To give that context, long LRM, the previous state-of-the-art for feed-forward, hits a 24-point-near PSNR. That is nearly a full decibel lower, and visually it struggles much more with artifacts.
And what about the traditional per-scene optimization methods?
Traditional 3D GS optimization achieves a 23.60 PSNR, significantly lower quality, but the real pain point is that it takes 13 minutes to run. tttLRM is obliterating the runtime of traditional methods while simultaneously beating them on rendering quality.
And it gets even more impressive when you look at the post-optimization ablation.
Yeah.
A lot of modern pipelines will use a feed-forward model just to get a fast initialization and then run a few dozen steps of traditional gradient descent on the output to sharpen it up.
Right, which is pretty standard practice now.
Even when adding 10 steps of post-optimization, tttLRM stretches its lead over an optimized long LRM. It outputs significantly sharper and more detailed geometry, specifically in those high-frequency areas like foliage or intricate textures that usually trip up feed-forward models.
That happens because the initial fast weight representation from tttLRM is so geometrically sound. The post-optimization doesn't have to untangle massive structural disasters or floaters. It just focuses its compute on refining the high-frequency details.
All right, let's put on our critical researcher hats for a moment. We've been praising this architecture, but there's no such thing as a free lunch in machine learning. What are the limits of relying on a fixed-size neural memory for a massive, continuous 3D environment?
You hit the nail on the head. The primary limitation is the capacity bottleneck. The fast weights have a fixed dimension. In this specific implementation, 768.
Right.
The paper notes that performance degrades slightly on highly complex scenes. If you feed it a massive outdoor environment or scenes with incredibly dense high-frequency textures, that fixed capacity memory simply begins to run out of room.
It's the classic catastrophic forgetting problem inherent in any fixed-state RNN. As the sequence length grows into the thousands or millions of tokens, the fast weights are forced to forget the earlier tokens to make room for the new ones.
Yes, and the authors didn't just accept that limitation. They explored a very clever, training-free mechanism to fight this drifting problem in autoregressive settings. They call it the selective update mechanism.
I love this part. If we imagine a robotic drone navigating a house, it flies from the kitchen, through the hallway, and into the living room. You don't want it forgetting where the kitchen fridge is just because it's currently looking at a sofa. How do they selectively protect that memory?
To prevent the fast weights from overwriting crucial historical data, like the kitchen in your example, the researchers use the diagonal of the Fisher information. They compute this via an exponential moving average of squared gradients.
Okay, let's translate that Fisher information math into plain English for a second. It's basically the model keeping a running tally of which specific weights had the biggest gradients historically, right?
Exactly. It provides a real-time estimate of parameter importance. The model literally knows which specific neurons are carrying the load for the geometry it has already seen.
So parameters that are crucial to the current input are updated freely. But the parameters that the Fisher information flags as historically important, the ones storing the kitchen fridge, are pulled back via elastic regularization toward a historical sliding anchor.
Yes. So you are selectively constraining the updates, locking in the important features, and only writing to the unimportant parameters.
It mitigates the catastrophic forgetting of the 3D scene without requiring a complete retrain of the model. It is a highly effective, elegant way to stretch the capacity of that fixed-size neural memory.
It really is.
Let's summarize what we've unpacked today. tttLRM brings linear computational complexity to large reconstruction models by leveraging test-time training and fast weights. It completely sidesteps a quadratic memory explosion of standard attention, unlocking long-context autoregressive 3D generation.
And it successfully combines the immediate single-pass speed of feed-forward networks with the real-time, high-fidelity renderability of explicit formats like Gaussian Splatting.
The real takeaway for the field is the paradigm shift in the architecture itself. Using fast weights as a universal, compressible, implicit latent space that can be explicitly decoded on demand changes how we can build spatial pipelines. You are no longer bound by the limits of attention, and you are no longer bound to a single rendering format. It's an incredibly robust foundation.
It really makes you wonder about the next leap in spatial computing and robotics.
I want to leave you with a provocative thought to mull over. If we can now dynamically compress continuous streaming visual data into a fixed-size neural memory that updates in real time without forgetting its past, are we looking at the foundational architecture for how future robotic agents will maintain a persistent, lifelong 3D mental map of their physical reality?
It's wild to think about.
Think about a robot that never has to rebuild its spatial map from scratch every time it reboots, but just continuously updates its fast weights as it navigates the world for years. That wraps up this deep dive into the source material. Thanks for joining us on AI Paper Podcasts, and we'll catch you on the next exploration of the research pushing the boundaries of machine learning.